Assalamualaikum warahmatullahi taala wabarakatuh. Selamat tengah hari and good afternoon to all of you. May peace and blessing of God to all of you. So today we're going to look at the last chapters, right? That the faculty have designed for students. They take dynamic DH M2103 dynamics, and it will be the impulse of force, right? So I'm using this book from Professor Miriam, and the topic consider the impulse of force for particle system of particle, which normally regarded as a model of fluid flow, and finally the rigid body. So, so we have to look at the particle part topics first because it provides us the fundamental for these topics. Right. The way that I arrange the topics for dynamics, specifically for kinetics, that we start with the using equation of work and energy to solve problems, and actually the method actually based on the equation of motion or based on second law of Newton's. So the if you get the book, it starts with law, which is net force equal to the mass of the body times the linear accelerations. So the net force actually is summation of all forces acting on the body. So when we evaluate the forces actually is a function of a distance. And from that, when we do the integration of the forces with the distance travels by the body along the path, we get the work done on the body, right? So in that, we can determine the velocity, the angular velocity, and so on, right? From the magnitude of work and as well as the kinetic energy changes. Now we look at the concept of linear impulse. What does it mean, and what is a linear momentum? I think all of you have an idea about these two concepts, right? So when we talk about linear, means that you are looking at the motion which is in a straight line, something like that, right? And the figure here show a curvilinear motion. Here we don't look at the general plane motion or rotation, right? That include rotation in it. When we consider the impulse and momentum, we are looking at cases where the forces is a function of time. The author here, Professor Merriam, when he developed the equations, it based on the Cartesian coordinate systems, and the particle is having velocity, and then you can see that there is a symbol G there, that it will be represent the momentum, linear momentum, which is defined by the mass times the resultant velocity. And the author also plays the R coordinate system and the E, the tangential and normal coordinate system as well. And the velocity at the particle position is given by R dot on top of it, and the and it represents the rate of change of radial location. And for the impulse, we are looking at the two position. The T1 represent the initial time, the initial location, and then the particle is moving through the curvilinear motion up to t2 time. So it takes some duration there, and we can see that the force there can be varies with time, or it can be constant. And the initial velocity is given by v1, and the final velocity will be v2. And summation of force is given by the summation symbol with operators and the force F. This information actually is summarized of what I have said earlier. Um, and I also include the equation how we can relate the momentum, the linear momentum with the summation of force acting on the particle. As you can see, the equation 3.25 does not directly relate to the summation of force. The linear momentum actually is a time rate of the linear momentum that gives us the value of accelerations, right? The velocity, when we differentiate the velocity with the time, and we find that the summation of force is a function of linear momentum. When we look at this equation 3.25, when I mentioned that the force is a function of time, actually the is because we have changes of velocity um, that eventually leads to the change of the linear momentum. So this equation 3.25 tells us that the resultant of all forces acting on a particle is equal to the time rate of change, right? So you have a rate of change, and this one is due to the time of the linear momentum. So we have a particle that move in a certain direction, and this direction can, when we apply some force, it can slow down the speed, and it will also can change the direction of that motion. So the direction of forces is depend on that variation of motion, right? So, and then the equation suggests to us that the linear momentum is also a vector quantities. So when we have a vector quantities, we can express the linear momentum in terms of its component, right? And when we, it is very important for us to define the coordinate system in order for us to evaluate the summation of force acting on the particles. The unit of the linear momentum is kilogram meter per second or Newton second. Now the author then go to the linear impulse momentum principle in order to describe the effect of the forces acting on the particles over a period of time. We have the equation of motion just now, the second law of motions. Newton is described in terms of linear momentum. And due to the this linear momentum is only a function of time, right? So we can rearrange the equation and place the time duration, right? Period of time on the side or on the left hand side. So we obtain the total linear impulse, right? So when we have a summation of force times multiply with the uh, period of time that the force, all this force acting on the particle, it will give us the change of linear momentum of that mass. The single force acting for a finite period of time is called linear impulse of the force. Or in mathematics, it's quantified by the force, that single force, time the duration that this force is applied to the particle. Now I'm going to the equation. After we do the integration, so we have equation 327. We have the what we call the linear impulse applied to the body, or we just call the impulse integral, which is equal to the initial linear momentum of the body, the final linear momentum of the body minus the initial linear momentum of the body. And the left-hand side of equation 3.27, or the linear impulse applied to the body, to the particles, is a vector quantity. And delta G there on the far right represent the change of linear momentum. The differences between, so normally we take the final values minus the initial values. So the initial linear momentum is a linear momentum at time t1, and g2 will be the linear momentum at t2. And this equation is a impulse momentum equation in vector notation, right? So we can also apply the impulse momentum equation in the S coordinate system, or if you want to use the coordinate, the rectangular coordinate system, we can use the X component. We can break the vector notation into its component. So that is given in equation 327p.